Okay, so now let's look at this question on constructing open and closed hash tables, and you're given all these keys. Okay, so the hash function is given and you have given only 6 keys here, and some of you are asking then the hash function has 7. So what is the size of the hash table? The size of the hash table, as I told in class, is based on the value of the integer that is the divisor of your mod hash function. So you should be using 7 index values for a hash table. Okay, so even though I could give you any number of keys, especially in the open hash table, you could have 1000 keys or any number of keys. The number of index values you have in the open hash table will depend only on the divisor that you use for the hash function. It's simple, isn't it? Because anything that is mod 7, the remainder will be from 0 through 6. So you need only 7 index values. Okay. Alright, so let's see. So 4 mod 7 is 4, 13 mod 7 is going to be 6, 15 mod 7 is 1, 22 mod 7 is 1, 30 mod 7 is 2, 18 mod 7 is 4. So it's now trying to insert all of them in this open hash table. So 4 can index into 4, so it inserts here. Then 13 indexes into 6, so that's going to be here. 15 is 1, 22 is a collision, which means you have to move further and index it here in this open, in this like linked list. Okay, and then 2 here, 30 gets here. Then 18 has index value of 4, so it gets in here. So the average number of comparisons for a successful search is going to be, if you want to search for any of these 4 keys, 15, 30, 4 or 13, you'll have to just do one comparison. So one comparison for each key times 4 keys plus 2 comparisons for each of these 2 keys. So 1 times 4 plus 2 times 2 divided by 6, which is 8 divided by 6, which is 1.33 comparisons. Now when will you have worst case number of comparisons? The worst case number of comparisons will happen if you are searching for either of these 2 keys, 22 or 18, which are out there, which means it's a successful search, or if you're doing for an unsuccessful search, and even in unsuccessful search you have to search for something that indexes to either 1 or 4, because only 1 or 4 has the longest linked list. If you index for something that hashes to 0, so for example, if you're even searching for 0 mod 7, it gets in here and there's nothing over there, so you can right away say that key is not there. Or if you're searching for even 7 mod 7 is 0, and you index into cell 0, nothing is out there, so you can say 7 is not there. So you have to search for something even in unsuccessful search that will end up being searched in the longest linked list, right, in the open hash table. So a key which will index into cell 1 or 4 which is not out there could be what? Anything that is a multiple of 7, with anything that is like 15 plus 7 is 22, which is there, but 22 plus 7 is what? 29. So if you search for 29, mod 7 is going to be what? 1, so you index into this cell, it's not there. If we search for even 8 mod 7 is going to be 1, which is not there. Similarly, anything that hashes to 4, so for example 11 mod 7 is going to be 4, it's not there. 25 mod 7 is going to be 4, it's not there. So you got the idea now, right? So anything that hashes into this longest chain, the linked list in the open hash table. Now in the case of closed hash table, the way we left the table is again the number of cells you have is 7, because the divisor is 7. In the case of closed hash table, the number of keys you can fill will be at most the number of cells you have. So here you have only 6 keys to fill and you have 7 cells, so that is fine. So let's see how these keys get fit in. So the first key is 4 indexes to 4, which is going to be here, nothing will be there initially, so you put there. 13 indexes to 6, nothing is out there, so you can put there. 15 indexes to 1, nothing is out there, you could put there. 22 indexes to 1, already 15 is there, so you have to move and put 22 over here. 30 indexes to 2, already something is here, so you have to move and put 30 over here. Then 18 indexes to 4, which is occupied, so you put 18 here. Okay, so you require, if you look at it, for an average successful comparison search, you will require one comparison for these three keys and two comparison for these three keys. So it is going to be 3 plus 6 over 6, which is 3 and 3 over 2, 1.5 comparisons. Now the worst case number of comparisons happens again for specific values. If you want to search for something that indexes to cell 1 and that key is not there, then you'll have to say, for example, you're searching for 8 and 8 mod 7 is 1, right? So you index it to a cell, it's not there, and you search all the neighboring cells, it is not there, and then you wrap around and then you see here it's not there. So you do 6 comparisons before telling it is not there. Okay, similarly, if you for the insert 8, you try to index into 1, something is there occupied, so you search in the neighboring cells, everything is occupied, then you wrap around and you search here, it's not there, then you can insert your key there, 8. So if you want to index, search for anything or insert for anything that hashes to index value 1, say 8, 29, right? Then well, 22 indexes to 1. So basically when you want to search, do an unsuccessful search, right? Yes, so when you want to do an unsuccessful search like 8, right, which indexes to 1, but you have to search all the way and then wrap around and then say it's not there, or you want to insert 8, right, then it will work. Anything that is not out there, okay, either you want to search for them or you want to insert them, you will require the maximum or the worst case number of comparisons. Alright, so now let's move on to this Huffman coding. So you're given all this code, so first sort them out. So D and E are the lower two values, frequencies, so you add them up, it is 0.2, and then B and C over here, so you could combine them, it's 0.4, then 0.2 plus 0.4 is 0.6, then this 0.6 plus this 0.4 for A will be 1, right? So now the left branch gets a 0, the right branch gets a 1, so in that way it is 0, 1, 0, 1, 0, 1, 0, 1. So A is 1, the path from the root to the node A, then B is going to be 0, 1, 0, C is going to be 0, 1, 1, D is going to be 0, 0, 0, E is going to be 0, 0, 1. So the average number of bits per symbol is going to be the code, the number of bits. So for A it's 1 bit and the frequency of its appearance is 0.4. So 1 times 0.4 plus 3 bits for each of them, so times the frequency of their appearance, 0.2 plus 0.2 for B and C, and 0.1 and 0.1 for D and E. So all add all of them. So 0.4 plus 0.2 is 0.6 times 3 is 1.8 plus 1 times 0.4 is 0.4, it's going to be 2.2. So if you use fixed bits per symbol, so this is if you use Huffman coding. On the other hand, if you use fixed bits per symbol, we would need how many bits? 3 bits, right? Because you have 5 keys, so log 5 to the base 2 with a seal is going to be 3 bits. You need 3 bits to represent each of these 5 symbols. So the generic compression ratio is 1 minus 2.2 over 3, which is going to be like 26.7%. Now for the given text, which I gave you, right? So all we have to do is replace each of the symbols with the code, the Huffman code you came up with. So A will be 1, another 1, then B is 0, 1, 0, C is going to be 0, 1, 1, and so on. So if you count the number of bits you have 1 bit for A, so basically count the number of A's you have. So 1, 2, 3, 4 A's, so 1 bit for each A, so 4 times 1, plus how many B's you have, 1, 2, two B's, each B is 3 bits, right? Then you have two C's, so each C is 3 bits again. Then one D, each D is 3 bits. Then one E, each E is 3 bits. So you add them up, it's going to be 22. So if you use again 3 bits per symbol as a fixed length encoding, it would come out to be 10 symbols times 3 bits per symbol is going to be 30 bits. So the generic compression ratio is going to be 1 minus 22 over 30, which is 26.7%. Okay. Alright, so let me see if we can stop here.